everyone. The topic for today is current electricity. Let's start with the video as usual.
The simplest electric circuit is a light bulb and a battery. The battery creates a force pushing the charged particles in the wire, causing them to flow in a loop around the circuit. The number of charged particles that pass by each second is what we refer to as the current. The charged particles flow through the light bulb because the battery causes them to have a higher potential energy on one side of the light bulb than the other. This is similar to how objects at higher elevations have a higher gravitational potential energy. This potential energy is what we refer to as voltage. If we visualize the potential energy as boxes that are attached to the charged particles, then we will see that this energy is converted into light as the particles pass through the bulb. The charged particles regain their potential energy as they move through the battery, which pushes the charged particles to the higher potential. When the energy inside the battery is depleted, the battery will no longer be able to create this potential energy, which we call voltage. A battery that has not yet been depleted ensures that the voltage between its two terminals is always at a specific value. If we place several batteries with the same voltage together in parallel, then this will result in more energy that is stored, and this will give us more time before the battery is depleted. If we instead place these batteries in series, this will cause their voltages to add, resulting in a much higher potential energy for each charged particle. A higher voltage across the light bulb means that a higher current will pass through it. This will cause far more light to be emitted by the light bulb, but it will also mean that the energy in the batteries will be depleted much faster. Much more detailed information about voltage, current, and electric circuits is available in the other videos on this channel.
So, we are studying current. So, actually, what is current? You just saw the video now. In video, they have clearly shown that it's actually rate of flow of charge. That means how much electrons flow in a given time is called current. So, current is written by I, and charge flowing in a given time is always called as current. So, you know, charge can be any. So, it's any by T as well. We all know E is going to be 1.6 into 10 raised to the power minus 19 coulomb, which is always a constant value. So this is the current in a given circuit, flow of electrons, and the unit for current is ampere. We can see this A written there. But some places we can measure in small values like milliamperes. You can see an MA written in your ammeter and microamperes. So if it's milliampere, it's 10 raised to minus 3. You have to multiply. If it's this, it's 10 raised to minus 6 amperes. That means if I say 100 milliamperes is the value you got, it should be equal to 100 into 10 raised to minus 3 amperes. So this is the way to convert. So this is in ampere is a unit for current. So first thing is current is flow of charge in a given time, and the unit is this. That's the first thing. Now next, this current can be given in any form. For example, current is flow of electrons. No, so even if the question is going to be an electron, an atom has got nucleus, protons, and electrons going out of the nucleus. So you can see electrons are moving in this wire. When electron move, its motion of electron is going to be current only because it's a flow of charge. So a current electron going around an atom is like current only. So you can say a current is a circular current carrying coil. An atom is a circular current carrying coil. So what will be the, let's see, we have the velocity of electrons. Let's imagine now the velocity of electrons given to us. How can you find current? So the radius of the electron flow is also given. What radius it's flowing at, what radius the electron is moving around. So the current is going to be charge upon time is okay, we know that. This T is the total time taken to finish complete cycle. So I can change time now because time is distance by velocity. So the total distance traveled by the electron to complete one circle is 2 pi r, we know circumference of circle, and divided by velocity will be time. So time, because you know velocity is distance by time. So take this V up. So QV by 2 pi r. This is your current. So current can also be given with this formula where I equals to QV by 2 pi r. So these are different type of questions they can ask you. So they give velocity, you can do that as well. And from here, 1 by T is called frequency. I can even say current is charged into frequency as well, because frequency is 1 by T. So different formulas for same current. So you have to know anything asked, you can easily find out the value of current in different forms they can ask you. Now once you know current, we know current is flow of charge. Once you know it, now we have to now get into the motion. Basically, this chapter, if you see, we have the basic information, which is your Ohm's law. What he did, he just made a current to flow in a circuit. So the Ohm's law circuit is going to be, let's take a circuit now. We did this in 10th standard as well. So we have a rheostat, we have an ammeter, and we have a resistor to connect or measure the voltage. We have voltmeter. So this is a circuit of Ohm's law, and rheostat is used to control the flow of current. So just make the circuit to work. You'll see some ammeter reading. You will see some voltmeter reading. Now move the rheostat, and for different value of current, find the different value of voltages now, or different value of voltage, find the current now, and make a voltage and current value in a table. What you see will be, you see the values are going to be directly proportional, or if you plot a graph, for example, V and I or I and V, then it will be a straight line. So what Ohm's found out was, if a current flows through a circuit, clearly the current in the circuit always depends on the voltage or the potential difference across the battery connected. So V and I are always proportional, and for him, V and I graph is a straight line. And if you make a slope, or you take a slope of the graph, then this graph will have a slope which is equal to, slope is always going to be equal to tan theta. And the tan theta here will be a constant. So he said the slope of the graph is always a constant. So if it's going to be, if this is V and this is I, then the tan theta value will be V by I. So this is what he found out, that the slope is always constant. He also found out that according to his law now, V is always proportional to current, but he said at a given temperature, pressure, and standard conditions. So the most important point he said is temperature should be constant. So for him, V and I are proportional, or when you take your V to proportionality out, you would have to put a constant. Now this constant according to him is called R, and this is called the resistance of a given wire. So he said V and I are proportional, and V is equal to IR, or your R will be equal to V by I. So he said this is constant because V by I in this slope is tan theta. It's a slope, it's a constant value. So according to him now, V by I, if you plot, it's a straight line, and the slope gives you V by I, once again R. So slope of V by I graph always gives you resistance, which is R, and which is always a constant value according to Ohm's law. But the problem is, it's only at a given temperature. He gave a very small important information now, it's at given temperature. Why given temperature? Because if you start plotting the graph practically, this graph will not be a straight line. After some time, the graph may start curving and going off like that. That means resistance will not remain constant for a long time. So resistance gets affected with temperature, because he found this was a very confusing information when he was doing the experiment now for a long time. He found out it was going on smoothly. After some time, he saw the R value changing now. So it is a confusion. So he has to now find out what is the problem now. Let's find out that why is that the R value is changing as you go for some time, or why is that you get a change in resistance. So first thing, practically speaking, when you pass current through wire, the wire gets hotter. So one thing is very clear, when you pass current through wire, heat is produced. So the first thing we should understand, you have a heat produced when you make a current to flow through a resistor. When current is flowing through a resistor, then heat is produced. So this is the first information now. So heat produced, basically heat is a form of energy. So energy is lost. So where is this energy coming from? So if I say heat is produced, means where is the heat coming from? So this heat, as it's produced now, is changing temperature. So the information he got was resistance was getting affected by temperature. So as the temperature goes up, resistance also goes up. So our curiosity now is, what is resistance? So this is the question we have to answer. When you get the answer for this, we may get information for, of course, why you have changing resistance with temperature and all the other things. So let's find out what is resistance. For that, we should go back to the basics. First of all, if you pass current through a material, in every material, current will not flow. There are materials which are called conductors. So in conductors, the current flows. But if you make a current to flow through an insulator like a wood or plastic, current will not flow. So why is that current flows in a conductor, not an insulator? So we know that answer before, because conductors have got free electrons. So they are the ones which move when you pass a connector battery to it. Now imagine a conductor. Let's imagine we take a copper wire. Nothing, just a copper wire of some length here. And this copper wire is just lying in the table. So nothing is there. The copper wire is placed. So what will be the condition for the electrons which are inside the wire? Because the electrons are there, free electrons are there. They are not attached to the atoms now, but they are free to move. So are they at rest? Or what's happening? So the first information you should know is, when you see a conductor placed in a table without being disturbed, the electrons inside the conductor are not at rest. That means these electrons which are inside the conductor are in random motion. So they move in all possible directions possible. I'm talking about all the electrons now, not one. Everything is moving in different directions. So electrons are already moving. So we studied now when electron moves, it's called current. So in a conductor which is not being connected to a battery, electrons are already moving now. So why don't you feel a shock when you touch a copper wire which is lying on the table? We are not getting a shock. We get current only when there's a battery connected now. Then how come we say flow of charge is current? So we have to check that as well. So let's find out what's the reason now. This electron, maybe one electron goes towards right, one electron goes towards left, or even this electron goes towards right and come back and go this way. That means random motion means they're not going in one possible direction now. They may end up going in one direction, come back. So I can see the velocity vectors of the electrons are in all possible directions now. So this velocity vector, maybe with velocity u1 maybe, and this velocity vector in the opposite direction. So there are velocity vectors everywhere. So what happens is this velocity vector and this velocity vector cancels out, and this may cancel out. That means if you take out the average velocity of all these electrons now, it may be almost zero. That means they found one thing now, even though they are moving now, they are not moving in one direction. They are randomly moving now. So one towards right, one towards left. So all these velocity vectors are getting cancelled out. So they considered the electron to be at rest only. That means even though they are moving now, they are not moving in one direction. So we consider the initial velocity inside a conductor to be zero, because they are not going in one direction. One velocity vector is this way, that way. If you start putting the values here, 1 is plus, 1 is minus, 1 is plus, you may get answer 0. So we consider to be at rest only. So that's the reason why it's not going in one direction. You're not getting a shock when you see a conductor lying on a table. Now this is what happens. Electrons are moving now, but in random motion everywhere. Now what happens when you connect this conductor to a battery? So let's take the conductor, connect it to a battery. So you know battery has got a positive and negative plate, and the bigger plate, this one is positive, this is negative. When you do this positive plate and this is negative plate, so these are positive charges now. So electrical field is set up in this direction from plus to minus. We all know electrical field is always from plus to minus. Electrons being negative, electrons are not moving in all directions now. So this plus plate will pull electrons in this direction. That means every electrons are now being pulled towards one side. When I say electrons are pulled, there's a force experienced by the electrons. So one thing is very clear now, electrons are not going to go at one speed, because if I apply a force now, there will be acceleration. So electrons are now going to start off with some speed now, and this is going to be pulling it constantly. It's like, drop a stone in air, it goes down, and as the stone goes down, it gets faster and faster. Reason simple, because Earth is always attracting it now, so the force gets bigger and bigger and bigger. So if you see that way, these electrons are pulled in one direction with a constant force plus now. So actually speaking, these electrons should start getting faster and faster and faster, and should go and bang on this plate, positive plate. But actually speaking, if you see the speed of electrons inside the conductor, it's very, very, very slow. So since we can't see electrons now, it's something confusing now. So if you see theoretically what we studied from your Newton's law, there should be an acceleration. Acceleration means speed should go up. If speed goes up means the particle should get faster and faster. It's the same story like you drop a stone from a height. So why is that here it's not getting higher speed or it's getting accelerated now? So you see the issue is very clear now. There are different problems now. Electrons are moving in all possible directions now, number one, and you're pulling it now. So some electron may go that way, they are pulled back. So some electron is already moving in this way, they are pulled back. So every electrons are in different site of motion now. So if you pull it now, they get different speeds now. So every electron in this conductor are now being pulled in one direction at different speeds. So the velocity of the first electron will be v1, second will be v2, v3, v4, like that. There are n number of velocities now. And these electrons, imagine they start moving. Imagine the first electron is moving here, this way, and the second electron is somewhere here, and it's also moving in this direction. So this is moving at velocity v1, this is moving at velocity v2. Imagine. The interesting thing is, as they move, the conductor is not having a free space. It's not like, it's a highway with nothing there so that you can go faster. There are so much of atoms and ions and everything in between. It's a packed area now. So this electron, when they start moving, beach may there are lots and lots of atoms and everything coming in between, ions now. So these electrons, when they move, they saw some obstruction in between. There are people standing there, So when it moves now, beach may something comes in, so they have to hit that which comes in the space. So in between, when they move now, something obstructs on the way and you have a collision. So these electrons are not moving freely towards a positive plate in the first story. So as they start moving, because of a lot of obstructions now, they get hit or have a collision. Whenever a particle have a collision, they slow down or stop. So this electron, which is taking off at maybe at after 1 minute or 2 minutes now, let's take at 5 minutes, this electron comes across another ion and hits it and stops. So this electron is now gaining velocity as they reach here. So it's being pulled by this thing now. So the electron is now moving and hitting to reach a velocity v1. And the same story for this electron now, but we can't tell the same story that, okay, this electron will also move for 5 minutes now. So this electron may move less distance, less time or more time because the atoms are not filled exactly. So it may move maybe for 3 minutes or 2 minutes and have a collision or maybe more. So every electrons are now moving in this direction and starting from 0, they are gaining speed towards V. And as they reach V, they have a collision. So they have a collision and they are going to stop or they're going to slow down. So they may have a speed. Let's not take V stop now. So it's gaining a speed as at collision now. So at collision, they're reaching a speed of V1. So this V1 is after moving a distance of T1. So if I ask you what's the velocity of first electron, it will be V equals to U plus AT is U1 plus AT1. I'm not putting A1 here because acceleration is constant. The next will be moving, will have a velocity, reach a velocity V2, which will be U2 plus AT2. So if you see that way, every electron are now going to have different speeds after collision. So they will be hitting, some will be 0, some will be something. So they may have different speeds now. So if I ask you what's the speed of electron in a conductor, electrons the speed again, I don't know because everything is having different speeds now. So like I took average of all this U1, U2's of initial speed which made it 0 now. I will take the average velocity of all this velocities of all the electrons now. So the average velocity of the electrons inside a conductor, if I ask you, that is always called as your average speed called Vd. This is called your drift speed or drift velocity. So the problem we are facing here is electrons are moving at different speeds. The electrons are reaching different speeds after collision. So because of that, the speed of electrons cannot be a one value. So if I ask you what the speed of electron now, it's going to be like different values are coming into picture. So they have to be taken the average value. So if you take the average of all the speeds now, then you get something like average speed. And this average speed is always called as your drift velocity. So drift velocity is the average velocity with which electrons move in a conductor, and this drift velocity is always very slow. So that's a very important thing. It takes very less time, very great time to reach a small distance now. It takes so much of time now. That's a big problem. And since v is u plus at, that's a velocity basically. So let's v be the average speed of all the electrons now. So v1 plus v2 up to vn by n will be equal to, this is u1 plus u2 un by n plus a, as I said, is constant, but t is also different now, t1 plus t2 tn upon n. So they have different speeds now, so the average of that, the initial average speed is 0. So this is called Vd, and this is 0. This is acceleration, which is going to be force upon mass. So this is the average time taken between collisions. So average time taken between collisions also has got a name now. It's called tau. So tau is the average time taken between collisions. This tau is called relaxation time. So relaxation time is once again the average time taken. So it's an average speed, average time, and a constant acceleration mass. So force is basically QE. So if I put F is QE here, it's because F by Q is always going to be electrical field. We know that in the first chapter. F by Q is E, so F will be equal to QE. So put a value here. So I get Vd equals QE by mass into tau. So if you take one electron now, Q equals to Ne, N is 1. So my Vd becomes, this is E. Q is Ne, so this becomes E. So Q is equal to Ne and N is equal to 1. So N is 1, Q becomes E. So this is a formula for your drift velocity of electrons in a conductor. So drift velocity is always given by Vd equals to E. This is charge of electron, E, electrical field, mass of electron, and the relaxation time basically. So if you want to make it a vector sign, basically if you want to put a vector now, it's going to be minus, because electrons always move against the electrical field. So this is going to be the vector form for drift speed. The one information which is missing here is electrical field is basically voltage upon length. So drift velocity has got another formula now, which is going to be EE. In place of E, I can put V by L tau. So if you check the formula now, drift velocity gets affected by length. That means if you increase the length of the wire twice, drift velocity becomes half. So length matter is not there in this E. So you should not get confused and say when length is double, nothing happens because drift velocity there's no L now. So length is there because E is V by L. At a given voltage, when you change the length, drift velocity gets affected. It's inversely proportional to the length and directly proportional to the tau, which is your relaxation time, basically. So these are the small informations you should know. So drift velocity is V equals to E upon M into tau. So we know this information now. Current is charged by time. I understood that. Okay, good. And drift velocity is the average velocity with which electrons move, and the formula for the average velocity is VE upon M into tau. And V is also equal to IR. So these are the things we know. Apart from that, this resistance of the resistor. What is the resistance? Basically, we saw because why electrons could not flow freely. So if you check into the matter of resistance there, when electrons move, there's a collision happening. So the obstruction here is because of the collision only. So this collision inside a conductor is basically resistance now. So resistance of a given conductor depends on the collisions they have. So more the collision they have, more slower they have to go, so current cannot flow freely. And our question number 2 was, why is heat produced? So simple logic now, electrons were moving at different speeds. They were gaining speed. So they were having kinetic energy half mv square. So they were already gaining speed and they are at a speed now. So suddenly what happens, collision slows them down. So because of this, electrons are slowed down and speed is being changed, what happens is there's a loss of kinetic energy. So this loss of energy due to collision is always seen in terms of heat. So you are seeing heat in a conductor mainly because of the collision happening in the conductor. So more the collision happens, more the heat produced. So clearly a resistor will have heat when you pass current, because when you pass current, the electrons are moving, but they don't have a free motion. They have collision with each and everything on the way. So because of collision, the speed changes now, so they lose energy, and that energy is seen in terms of heat. So resistance gets affected due to heat, temperature. That's the first information. So more temperature, more resistance. Or resistance is more, temperature is going to be more. Or if you increase temperature, resistance gets affected, because when temperature gets more, the electrons tend to go faster. So electrons tend to go faster, then they'll start crossing that given gap faster. So there'll be more collision at a given time. So that's also say there you can see resistance get affected by temperature. So what are the factors your resistance gets affected? They find out this now. Resistance gets affected because of the length of the wire as well. So more the length, more the resistance. That means the path of resistance is more. So there's more and more construction happening on the way. So current gets affected in the wire. Resistance get affected by area inversely. So bigger the area, more the resistance. It's like, smaller gap, more gap. There's a lot of gap to move. So these two factors also affects resistance now. So more than temperature, resistance is affected because of length and area. So if you combine these two values, take it out. These two values you take now, resistance at a given temperature is going to be equal to rho L upon A. So rho is a constant here. This rho is called resistivity of a given wire. This resistivity is also called as specific resistance. So you should know the name. So specific resistance means resistivity only. So it's a constant value for a given wire. So copper has got a constant resistivity. So you should not. So resistivity is a constant value. Resistivity gets affected only by two things now. Resistivity gets affected by temperature, and they get affected by material, nature of material. So if you change the material, resistivity gets affected now. So copper ki jagah pe use your silver, you use aluminium. Resistivity is different. So resistivity depends on material and temperature. Why I'm telling you this? Because from this formula now, resistivity will be Ra upon L. So you should not say that, okay, resistivity gets affected by area and length. Area, length, you do anything now, resistivity gets constant. So resistivity of a given wire is same. That means a 1 meter copper wire and a 10 meter copper wire has got a same resistivity. So resistivity should not be affected. So it gets affected only by temperature and this thing now. So resistance get affected because of this. So these are the information you should know. And if you see the resistivity, and so resistivity gets affected by temperature as well. And 1 by resistivity is always called as sigma. This is called conductivity. So when I say resistivity or reverse is conduction. So 1 by resistance is called G. This is called conductance. So these are the 10th standard information now you should know. So 1 by resistivity is conductivity and 1 by resistance is conductance. So resistivity, temperature are proportional. But there's a very important information you should know. Resistivity and temperature are proportional in conductors. Copper, silver, conductors, they are proportional. In semiconductors, resistivity and temperature are inversely proportional. So you got to be very careful now. This is for conductor, like all copper, silver, and this is inversely proportional to temperature in case of semiconductors like diodes, transistors. So if you see the graph for a conductor, resistance and temperature graph for copper, the graph is going to be it's proportional. It's going to go up. So this is for a conductor, say copper. But for silicon, if you see, the graph is going to be like this. This is for silicon. So you got to be very careful about the graph. So resistance temperature graph is directly proportional for copper and inversely proportional for your silicon mainly. And if in between there are something there, so there's a conductor there, there's a semiconductor there, there are resistance wires called manganese, constantan, nichrome. These are alloys. These are high resistance wires now, resistance wires. So normally these are resistance wires. That means when I say resistance is there, they are not going to allow the current to pass through properly. But in all your instruments like meter bridge, potentiometer, even Ohm's law, everywhere the wires used are based on these things only. So these are normally used in your instruments. I'm just telling two things now. One is I'm saying it's a high resistance wire, so current cannot flow through freely. But I'm saying they are the ones who are preferred. So what's the reason that this is preferred compared to copper or silver? So question is why in meter bridge or a potentiometer machines now the wire used is not copper but manganese. The reason is very clear now. These alloys normally have the same problem of resistivity proportional to temperature. It's okay. If you see the graph of resistivity and temperature of alloys now, it's not going to start from zero because they already have some resistance now. So they have resistivity already there, rho naught. So this is going to be the graph for manganese or constant tin, number one. And second thing, why are they preferred? The logic is very clear. Resistance and temperature are proportional. So with temperature, resistance always goes up. In case of copper, the temperature changes much faster. But in case of manganese, constant and nichrome now, with change in temperature, your resistance is not going to change that fast. Or in simple logic now, there is something called temperature coefficient. So temperature coefficient is something which will decide how fast the temperature will affect resistance. So copper, silver have high temperature coefficient. That means with temperature, they are very sensitive. Temperature resistance will change very fast. But in case of manganese, constant tin and nichrome, these things are having a low temperature coefficient. So the interesting information you should know is with temperature, the resistance are not going to get affected that faster compared to. So in normal machines now like meter bridge or Ohm's law, we use this because when we take a reading in your practical lab, the resistance is not going to be affected that much because you can use it for some time. So it's not going to affect much of your values when you take a reading practically. So because temperature is not going to affect resistance here in this case. So why manganese, constant and nichrome are used? Because they have a low temperature coefficient and high resistivity. So low temperature coefficient means that with temperature, resistance is not going to get affected much more. I will not use copper because they have a high temperature coefficient. I will not use semiconductors because they have a negative temperature coefficient. With temperature, resistance will decrease. So that's going to be dangerous. So semiconductors are not used. So resistance and this thing is proportional. We got the information now. So let's find out the relation between current and drift speed. So I would go for a relation between current and drift velocity, I and Vd relation. So for that, what we do, we consider a wire, length L, area of cross section A. So electrons are moving in the wire and they've got a drift speed V. So the current we have to find out for this wire will be charge upon time. So this is something we know. Charge upon time is current and charge is Ne. Ne is number of electrons in the wire into E by T. Now this N is a number of electrons in this wire. So this N value is not a constant because I have a copper wire. Maybe first I'll take a length of 10 meters, then I take 1 meter, then I have 5 meters now. So depending on my length, now the number of electrons are going to be different. So this N cannot be a constant value. So I cannot have a proper value for this. So I need something which is constant here so that I can use it here. So I need to find the number of electrons in any wire I wanted or any wire I go for, not the wire I have. So let's imagine or let's consider small n to be number of electrons per unit volume. This is called number density. So if you ask what is this actually basically is, imagine this copper wire is some 30 cubic centimeter. I'm finding out the number of electrons which are present in 1 cubic centimeter. That means out of this copper wire, consider 1 cubic centimeter copper wire size. In this 1 cubic centimeter, how many electrons are there is what I'm finding out. So I'm not finding out the value for the complete wire. I don't know what the volume of the wire is. It may be anything I wanted. I'm not bothered. But I'm finding out what will be the electrons that are present in 1 cubic centimeter. So I take a 1 cubic centimeter copper wire. In that, how many electrons are present? That gives you this value. This is called number density. Once I know this, So volume is area into length, because pi r square h is a volume now. So area by length, area to length. So the number of electrons in a conductor will be NaL. This is constant for every material now. For example, copper has got a number density which is constant. Silver has got a number density which is constant. But A and L is your problem now. You take any area, you take any length now, your number of electrons you can find for any wire now. Since this is constant for everything now, I know this value. You take any wire you want of any area, any length. Now multiply that to this, I get number of electrons for any wire I wanted. So this is the thing I did. I removed N and I put a value which is going to give me for everything now. So that's a idea of changing the N value. So instead of small capital N, you put NaL. So my current I will be equal to NaL E by T. Because this is NaL E by T. And length by time is velocity, which is average speed drift velocity. So NaE Vd. So this is going to be the current formula now, because length by time equals velocity. So current is always going to be equal to I equals to NaE Vd. So this is the very important relation now. So what we're getting now in this is current and drift speed are proportional. So I proportional to Vd. A very important information. So more the current, more will be your drift speed. If I take the area down, so imagine I take current by area, then I'll have a formula NeVd. This current upon area, this is always called as current density. So there's another name now coming into picture. There's something called current density, which is current per unit area, and this is denoted by J. So current is normal I, and J is current by area. So current is ampere. So here this is going to have a unit ampere per meter square, because area is meter square now. So unit numericals, you can easily make out what is the question given. It's ampere means current, and ampere meter square is J value given to you. This is NeVd. So I is NeVd and J is NeVd. So this is the values you know. So there's a new name you're getting now, current density, current upon area. So current and Vd are proportional. So the formulas we did just now until now is these things now. We did I is Q by T. And also I is NeVd, and we did Vd equals to E upon m into tau, and R equals to rho L upon A. So these are, so which way we should know what is done before, because if you want to use the formulas now, you should be remembering what is being done. So these are formulas we did. So current is charge upon time and these things now. We're going to apply this. So let's do one thing. Let's go to that same equation of I equals to NeVd. So I equals NaV. Let's use this formula. Now instead of Vd, I'll put the formula what we got before, and the formula we got for Vd will be NeA, which is E upon m into tau. So I'm using the formula of Vd, which has already been found out. Now this is E, this is E, so I get a value of N, and E into E is E square, Ne square tau by m. Ne square tau by m, then A and E. A. So I got all the values now. Ne square tau by m, E by. Now instead of E, I put V by L, because E is V by L. So Ne square tau by m, V by L, A. So I'm putting E equals to V by L. So now what we do, V and I, we take V and I one side, everything that side. That means you take I down, so I comes down. ML goes up, so I comes down, I get V by I in one side. ML goes up, so ML goes up. So these things goes down. Ne square tau A. So ML goes up, Ne square tau A comes down. So V by I is called R. So I get R equals to M by Ne square tau L by A. So this is my equation number 1. But we know that R equals rho L upon A. So this is already studied. So let's equate 1 and 2, because both are R. So equating 1 and 2. What we get? So equation 1 is Ne square tau upon M L by A equals rho L by A. L by A cancel. So rho should be equal to M by Ne square tau. Sorry, M by Ne square tau. Now this is the formula for resistivity. So I we know that 1 by resistivity is sigma, which is Ne squared tau upon m. So the formulas now is getting more and more. So apart from the formula we did, we have got another formula coming into picture. M by Ne squared tau is called resistivity, and rho is Ne squared tau upon m. So this is the information. So we get this formula now, resistivity ka. Let's go for this formula J once again. It is NEVD. So J, I told you, is current density. NEVD, so E upon m into tau once again, which is Ne squared tau upon m, E, J. So this is, I just told you now, this is sigma. So J equals sigma E. J is current density, sigma is conductivity, and E. So if you make it a vector now, this is your vector form of Ohm's law. So if they ask you what's the vector form of Ohm's law now, J is sigma E, not V is equal to IR. So this is another information. So we have done these informations until now. So we did what is resistance now, we did what is Ohm's law, we found out what is drift speed, we understood what is resistivity of a given wire, we know what is temperature coefficient now, and we also know the relation for resistivity and conductivity and what's current density. So these are information we got. So these are the basic interior things inside the conductor. But actually, this chapter is all about the current flow in a circuit. For that, there are two things now. One is there are two type of materials you have. One is ohmic and non-ohmic device. So ohmic materials are normally the ones which follow Ohm's law. So you can see a VI graph will always be a straight line, which is I'm talking about conductors and your copper, silver, and all this stuff. So there are non-ohmic devices as well. There are devices which do not obey Ohm's law. So I can see the VI graph will not be a straight line. So if you see the graph of resist for diode now, this is a graph of current voltage diode. So it's not a straight line. So diodes, transistors, LEDs, they do not obey Ohm's law. So they are non-ohmic devices. So in this world, we have ohmic devices which obey Ohm's law. There are non-ohmic devices which do not obey Ohm's law. So there are VI graph straight line, not a straight line as well. So you can't always say it's going to be always the same. So this is the next information now. Ohmic and non-ohmic devices are also there, apart from all the values or the information we got. And also consider a wire of resistance. Take a resistance wire R. Let's take R1. You pass current through it. Heat is produced. With temperature, resistance will change. So let's imagine for a given temperature for a given time t, we are allowing the current to pass through. After some time t, we found out that the resistance is changed to R2. My temperature in the starting was T1 and it became T2 after some time. So at T1, my resistance was R1. At T2, my resistance was R2. So R2 and R1 are two different temperatures because the temperature has changed. Now, what will R2 minus R1 value depend on? The increase in resistance depends on what factors? That's our first information. So when you pass current through wire, heat is produced. So that heat will change the resistance now. So what are the factors which can affect the resistance of a given wire? So the change in resistance, delta R value, we can think of, depends on the first information, the R1, the original resistance you take. So whatever the value of resistance you have in the starting, that will decide how much resistance will change when temperature goes up. So the first thing is the resistance you have, uska resistance is more important, and the change in temperature. So the factors which affect your resistance is R1, the original value, and also the temperature difference, how the big temperature is going to change. So combine these informations now, R2 minus R1 will be equal to alpha R1 T2 minus T1. This alpha is called your temperature coefficient of a material. We just told how well it changes the temperature. So R2 will be equal to R1 into 1 plus alpha T2 minus T1. T2 minus T1 can be written as delta T. So R2 will be equal to R1 into 1 plus alpha delta T. So this can be RT and R0 as well. So you can have equations depending on the temperature. When this is at 0 degrees and temperature T, and R1 R2. So it's okay. So this is the relation for your resistance change with temperature and the original value. So these formulas are also important and you have to use. So we did what is your drift speed, what is resistance, what is Ohm's law, what is your uh, current density and all this stuff. So there's another word which is you need to know. It's called mobility of electrons. So these are the technical informations you should know. Mobility is denoted by mu. So mobility is always denoted as drift velocity per unit electrical field. It means in a given field, how much the drift will be happening. So if the drift is going to be more in a given field, we say mobility is more. Less means mobility is less. So if you see that way, in semiconductors, you have something called electrons and holes. Electrons and holes both move when you make a semiconductor connect. If you connect a semiconductor to a battery, electron and holes both are going to move. But the mobility of electrons are always more compared to holes. That is, in a given field, electrons will move more compared to holes. So there, this mobility factor comes a lot in that chapter called semiconductors. So electron and hole, if you say, electrons have more mobility and holes have less mobility. So drift velocity can also be written as mu e. So you got another formula coming into picture, I equals to NEAVD. This formula can also be changed and written I equals to NEA mu e. So these are a lot of informations now in formulas you got. So these are the formula you have to find out. I is going to be NEA mu e. So mobility is drift velocity per unit electrical field. So this is also okay. We've understood what is resistance, what is this thing. Let's go to the most important part of the chapter. That is, whenever you need a current to flow, we need a battery. So you need to know these information now. What is EMF and what is your terminal potential difference? This is a very, very important part of this chapter. So what does these two indicate is the most important information you should know. What's terminal PD, what's EMF? Imagine a battery and there are some resistors in a given wire. So this is a nice video you saw in the starting. So this is a battery, say 10 volt battery. So 10 volt is the energy this battery possesses for the electrons to go around in the conductor. So basically, 10 volt is the total energy you have so the current can flow. So this 10 volt is always called the EMF of the cell. The amount of work done to take the electrons around a complete circle is going to be your EMF. So this is the energy they possess, 10 volts. So if I say 10 volt battery, it's called EMF. So EMF as a battery is always the total value of this thing. And the negative plate and positive plate is always there. So this 10 volt for now, let's say that way. This 10 volt now. So let's take this is 0. Normally negative is 0. And this is, let's take this 10 volt. That means they possess a 10 volt energy. And we know volt is work done upon charge, which is joule per coulomb. So voltage is energy basically. Energy per charge. So if there is a loss of energy, then I should blindly say there will be a loss of voltage as well. So energy and voltage are linked because they have a unit already joule in the system now. So that's a condition. So these are resistance wires are connected now. These are resistance which are connected together like this. Now this is a 10 volt plate, and I've drawn like this, and I put some special line like this. So these are the points where you have resistances. That means all the other points there is no resistance offered. So we presume that there is only resistance offered in R1, R2 and R3. That means resistance, I told you, is already collision of electrons. So there is only collision happening in this, and they are different. So maybe they have different value of collisions now. Maybe R3 may collisions are more than R2. We don't know. So, but there's a collision happening here. It's like, you have a race. In the race, if you run, there are some obstacles kept here. So between obstacles, you have no issues now. You run. Energy is lost, but once you jump the obstacle from one to another, this obstacle may you lose energy. So first obstacle may be a smaller one, so you jump. But anyway, The energy you have here and energy you have to jumping the obstacle is not going to be same. So as you jump that side, you lost some energy. Then you start running. This obstacle, imagine, is much more bigger. So you have to jump much more, but you lose a lot of energy there itself. And last way, there's another obstacle there. You jump that and finally go and say fall down and say, okay, it's over. I finished the race now. So this is what happens in a conductor for electrons now. Electrons possess energy. They already have energy now. So every person have their own energy now. So they start running like this. But as they see the obstacles in every resistor now, they have to do a lot of work like collision. They have to have a lot of problems now. So they lose energy and then come out of that and still starts moving and finally reach this plate because electron go this way. So wherever you see resistance there, I can blindly say there will be collision and there will be kinetic energy lost in terms of heat. So I have a heat loss here, I have a heat loss here, I have a heat loss here, baki points mein nahi hai, as of now in this diagram. So 10 volt is my battery voltage. So until this point, I'm not losing energy now. So my 10 volt remains 10 volt only. I told you already, voltage is actually energy, joule per coulomb. So my 10 volt will remain 10 volt, so no issues at all. But as I enter the first resistor, I have collision, electrons have to. So this point, when they come, when the current reaches here, because of collision in the resistor, energy is lost. So you cannot expect same 10 volt here. It must have lost some voltage and must have reached and got 7 volt. That means 3 volt has got lost in this resistor. So what information we get is every time there will be a voltage drop. So this is called a voltage drop. Voltage is dropping. So between 10 and 7, between 2 points of resistor, there will be a potential difference. Because this is 10, this is 7, subtract, you do it, you get 3 now. So this is a potential difference between 2 points of resistor, and that can be measured. If you put a voltmeter here, the voltmeter will show you this value. So voltmeters are used to measure the potential difference across 2 resistors. So between R1, if I put now, my voltmeter will show 3 volt. And I can calculate V equals to IR. So my V on the, let's take this is V1. My V1 will be IR1. So that's a voltage drop in a resistor. So if I ask you what's a voltage drop now, voltage drop is always going to be IR. So IR1 is a voltage drop in this resistor, which is equal to 3 volt. Now, 7 volt is still there. So that 7 volt is still with you, no losses. Next goes the thing. Here it becomes, let's take 3 volt. So 4 volt get lost here. I've got 3 volt here, this is 0. So all the 3 volt has to drop here so that you come empty handed. Because energy cannot be created nor be destroyed. So clearly, you start with 10 volt, you ran through, and you lost some voltages. So you lost some voltage. So your V2 will be IR2, which is 4 volt. Your V3 will be IR3, which will be say 3 volt. When you add up 4 plus 3 plus this is 10. This is my EMF. So if I add all these voltages, now I should get EMF. So the voltage drop in the resistor total will give you the total battery voltage. So energy is not created, all the energy is used. This is the outside view, you say. Okay, very good. So we got resistors here. These resistors are connected outside the battery. So they are called external resistors. So my capital R is called an external resistor. External resistor. But one resistor we can't see is the resistance inside the battery as well. Because every battery has got electrodes, you have ions, you've got liquid, which are electrolyte. So there are resistance offered in the metal, viscosity. So there are resistance offered inside the battery as well. So inside the battery, there's a resistance which is always there. We can't show inside, so I'll show it outside the battery now. This is inside the battery only, which is always denoted as small r. The small r is always called as the internal resistance of the battery. So internal resistance, if I say small r, I'm talking about battery inside. When I say capital R, I'm talking about battery outside. So 10 volt was my AMF before. I told you already now, when you have a resistance, there's a loss of energy. And there's a resistance inside the battery as well. And for a new battery, if you buy it new, the internal resistance is always very, very small. But as the battery is used for a long time, the small r value gets bigger and bigger and bigger. So starting May, you will not expect much of the wastage happening. So 10 volt is there with you. Imagine current starts flowing. The first voltage drop happens inside here because there is a voltage loss going to happen because there is a resistance offered inside this also. So I've got a voltage inside my battery. This is going to be equal to I into small r. So I've got a voltage drop inside the battery, I small r first. So out of 10 volt, imagine now 1 volt has got lost. So 10 volt was my total battery voltage and 1 volt has got lost inside the battery. So I've got only 9 volts with me now. So whatever current is going to flow is because of 9 volt only, not the 10 volt. So this plus plate will not be 10, will be 9 only. So the battery voltage is 10 volt EMF, but I have only 9 volt in my hand. So this 9 volt is the potential difference between the plus and minus plate now. So this 9 volt is always called as your terminal potential difference. So you should know the difference between your terminal PD and the EMF. EMF is always going to be the battery voltage the battery possesses when you are not in use, or when you have a battery in your hand of 10 volt, I can say it's EMF. It's called electromotive force. But as the battery starts working, because of the resistance offered inside the battery, some voltages get wasted and you have only some left out voltage available for the current to flow. And that left out voltage is always called as terminal PD. So terminal PD can get lesser and lesser as the R value gets bigger and bigger and bigger. So a new battery will have a good terminal voltage, but as the battery gets older and older, the terminal voltage also starts getting bigger and bigger. That's smaller and smaller because voltage drop gets more and more. So my 10 volt was my voltage EMF I had. 1 volt got lost and I've got 9 volts. So this 9 volt is called your terminal voltage. This is E and this is my voltage drop IR. So V is always going to be equal to E minus IR. So E minus IR, so terminal voltage formula is always going to be equal to EMF minus the voltage drop inside the battery. So what are the conditions we get from this now? When I is 0, that means when there is no current flowing in the circuit. When I is 0, then E will be equal to V. So your terminal voltage and your EMF will always be same when battery is not in use. When battery is in open circuit, then the terminal voltage and EMF is always going to be same. Then V is E minus IR is okay. So there is another formula now. V will be equal to E plus IR. So we have to be very careful here. This is terminal voltage E minus IR. This is also terminal voltage E plus IR. Now when will I use this and when will I use this? So you should know this. This formula will be used when your battery is discharging. And this formula will be used when battery is getting charged. So now we should know when is this charging happening, when is this discharging happening. So this is another story now. So we can have E is E minus IR or E plus IR. So I will use this formula when my battery gets charged, and this I will use when battery is discharging now. So let's understand what is the way of finding out when it's getting charged and discharged. So I'll give you two circuits now. So there is this one, there's a resistor here, there's another battery like this. This is a 10 volt battery and this is a 2 volt battery. Now next one, same 10 volt battery. Resistor, let's have the same resistor here. This is also connected, 2 volt battery. If I ask you what's the difference between these two batteries now, you can say clearly. First of all, in a battery, current always goes from plus to minus. Even though electrons flow is current, we always take them plus to minus because that's a convention they taught in the static. And number two, electrical field is from plus to minus. So this is a plus plate, this is a minus plate. This is a plus plate, this is a minus plate. So this is a plus plate, this is a minus plate. This is a minus plate, this is a plus plate. So if you see here, the current for this battery will be from plus to minus. So plus is this, so plus side goes up and it goes towards minus this way. So this is my current for this battery, which is I1. Let's take that. Now for this battery also, current goes in this direction only. Let's take this is I2. So this battery sends a current I1, this sends a current I2. But interestingly, what happens now? Both are sending current in the same direction. And normally in a circuit now, current will be depending on every battery together. So there will be one current only. So this will not be I2, it will be I1 only. But both the batteries are now helping each other. Both of them are now making the current flow happening. So if I ask you the total voltage of the circuit now, the total EMF, because both of them are now helping each other. Or in simple terms, if you see current on both the batteries getting in same direction. So take a pencil and draw current. Current is from plus to minus. So current of this is also going this way, this is also going this way. That means they are helping each other. The total EMF becomes 10 plus 2, which will be equal to 12 volts. So it's very easy here. They are helping each other. Here both the batteries are sending current out. So both the batteries here are discharging. So I have no confusion here. My discharging is happening. So every time current goes out of the battery, it's discharging. So both the batteries are discharging. So this will be V1 equals to E1 minus IR1. This will be V2 minus IR2. So here both are going to be V is equal to E minus IR1 because both are discharging. But I have a situation here. The plus plate is now sending current in this direction. So this is I1. So current goes this way. But here the current is going in this direction. Oh. So current here is this way, current is this way. How can current go in two directions now? So in a circuit now, current will always go in one direction only. So whenever you have a situation like this, so whenever you have a circuit where you start drawing current in your pencil and you saw one battery current is going right and one reverse left, means they are going in opposite direction now. Then what happened? No confusion. The bigger battery always takes charge. So current is going to flow in this direction only, this way, but the net EMF of the circuit will be, you have to subtract both the EMFs. So EMFs will be, net EMF will be E equals to 10 minus 2, which is 8 volts. So understand the difference between these two circuits now. Here both are sending current in the same direction, so they add up. Here they are in opposite direction now, they get subtracted, but the bigger battery only makes the current to flow this way. But in this process, this battery is anyway sending current out, so it's discharging, so no confusion at all. But this battery is now getting charged. So if you have two batteries connected in the opposite direction, or you see two batteries where current goes in opposite direction, then the smaller battery will always be getting charged. Or I can say the smaller battery terminal voltage will be V equals to E plus IR. So understand this very clearly. When you see a circuit now, take a pencil and you see both batteries in a circuit, draw the current direction from plus to minus. So if you see current, both are sending current in the same direction, you're happy, add them up. But they go in opposite direction, then you have to see to it that subtract the values and also tell yourself the smaller battery terminal voltage will be plus IR, not minus IR. So this is the very, very important information you should know. So numericals are there in your NCRT, so you got to be very careful about it. And also, I can give you questions like, terminal voltage and current graph. Say 6 volt, 3 volt, 1, 0. This is 0.1. This is 0.2. This is 0.3. The graph is given to you. This is a battery discharging, V and I graph. This is terminal voltage of the cell, and this is your current. Question is, find the EMF of cell. There's one cell there. It's sending current through. So then we have a cell of EMF E. There's a resistance here connected R. It's got its own internal resistance now, small r. So current flows in this direction. So current I equals to V by R. So I is going to be E by R. These two are in series now, so R plus R. So the current in the circuit will be I equals to E by R plus R. So I can say there's a current flowing now, and I've plotted a graph. What's the EMF of cell? So now from this graph I can find EMF now. So it's very simple now. V equals to E when I is equal to 0. We already studied that. So here when I is 0 here, my V value is 6 volt. So this 6 volt is going to be the EMF of the cell. So if you're given a graph like this and ask you what's the EMF now, the maximum value is EMF now. Be careful. Sometimes they give you 3 cells connected. Instead of 1 cell, there are 3 cells now. So all the 3 cells together are 6 volt. So 1 cell will be by 3. Right? Identical cells are given, then you have to divide by 3, so 2 volt is the answer now. So it's 1 cell I told, so 6 volt is the value. So you can find the EMF of cell in this graph very easily because when I is 0, the maximum value is EMF. Now I can ask you next question. Now from this graph, what's the internal resistance of cell? Cell ka internal resistance kya? EMF are found out. Well, what's the internal resistance of cell? I can easily find internal resistance now. From this equation now, when will I be maximum? Maximum current flows when external resistance is 0, when R is 0. So I max is going to be R0 equation mein, then you get E by small r only. So small r will be E by I max. Now here E is 6 volt. Maximum current is 0.3. This is my internal resistance of cell. So if I ask you internal resistance of cell from this graph, this by this you divide, maximum values दोनों को divide करो, then you get the value of small r, which is the internal resistance of cell. So you understood the difference between terminal voltage and EMF. EMF is the total energy of the battery, and terminal voltage is the total EMF minus the voltage lost inside the battery, is E minus IR. It can be charging, discharging, or no current as well. Now we'll go for the basic thing which you already done now, but anyway we'll do it: resistance in series and parallel. Resistance in series. So when you put resistance in series, what will happen? So we did this in capacitors, so we do the same thing here. There are three resistors now in series: R1, R2, and R3. We already done what's EMF and terminal voltage because of that. So there's no internal resistance here. Let's imagine it's negligible internal resistance now. So let's not have it. So when you pass current through it. So I just taught you EMF before, terminal voltage and voltage drop, because it's easy to understand now. So current flows to the first resistor. There will be a voltage drop across the first resistor V1. There will be a voltage drop across the second resistor V2. And there's a voltage drop across third resistor V3. If I have an internal resistance, I'll have a voltage drop there also. Let's have only these three. So my total EMF of the cell will be V1 plus V2 plus V3. So it's very easy now. The total voltage add karo EMF. So internal resistance nahi hai. The idea of doing series parallel I told you already now, because the series where there are three resistors now. The idea is to find the equivalent resistance. Equivalent matlab you remove the three resistors and put one resistor which is going to have the same effect of these three. So my idea is to remove this three and put only one. So the total value will give me V equals to IR. So I and R, this is series. I'm saying I because current is going to be same throughout the wire, so same current will flow through. So I. So V1 I told you already is IR1. V2 will be IR2 and IR3. I is same because it's in series, same current flows through. So take I common and cut. So you get resistance in series will be equal to R1 plus R2 plus R3. So this is the basic formula for resistance in series. You know that anyway. So this I'm just telling you because it's we should have done before. The idea of doing it now because voltage drop you don't know, so it's very difficult to say what happened. Why will this V1 come into picture? So this V1 is because the voltage across this is V1. We understood that nicely, so that's what it's easier to understand. This is in series now. So what about parallel? Parallel mein the difference is the voltage remain constant, current is same. Current is different. So it's parallel. So the resistors are 1, 2, and 3, and battery. This is R1, this is R2, and this is R3. This is EMF. The current I comes in and branch into three parts: I1, I2, I3. The voltage across is V. Terminal voltage is V, and V is same throughout. So in a parallel circuit, voltage remains constant. So your current here is branching into three parts. So I1 plus I2 plus I3. My idea is to remove all three and put only one resistor. So I equal to V by R. So V by R in parallel. V is constant, so same V will come into picture. R1, V by R2, and V by R3. So cancel, take common. So 1 by R will be equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is going to be the total resistance of the circuit in parallel. So in series and parallel, this is the information. So we understood now in say resistance series parallel, this is a condition. What if we put cells in series? And that too, these cells are going to be of same EMF. So let's imagine we put n cells in series. All have same EMFs E. And this is connected to external resistor R. All have internal resistance small r, small r, small r. So if I just told you we have all the cells giving current in same direction, add the EMFs. So here all the batteries are sending current in same direction. So I'll add all the EMFs now. There are n cells now. So total EMF of the circuit will be NE. And total internal resistance will be R plus R plus R, NI. So what happens now? This circuit is now become a smaller circuit. That means my battery is now made into one, NE ho gaya. And the total internal resistance is NR. And I've got a battery resistance connected to it, which is R. So this is my shortened circuit. So now I want what's a current? Total current is total EMF. Total EMF is any by total resistance. These two are in series now, NR plus R. So this is going to be the current in the circuit when you have N cells in series. This is the most important information now you should know. So N cells in series, the current is NE by NR plus R. If your R is very big compared to R is very small compared to NR, that means your R is negligible, then I becomes NE by NR, which is E by R. That means it will be equivalent to one battery sending a circuit only. So if I get my R very small and neglect it, then I'm going to get current because of one cell only. That means it's equivalent to one cell. On the other hand, if my R is very big compared to NR, NR is negligible, my I becomes NE by R. So it's almost like N cells ka value. So this is something you should be understanding it. So depends on the resistance and this thing. So now put cells in parallel. Same cells in parallel. That means you have same EMFs now. Cells in parallel. So you have n number of cells. Instead of n number of cells, now I'll put EMF E small r, E small r. Like that, you have m cells and resistor. The voltage is same. R. Now, if you have EMFs which are going to be hundreds of EMFs batteries now in parallel, the total EMF will also be E only. So you should not be confused about what I should do for EMF. Now EMF is E, because if you have identical cells which are connected in parallel, what one cell EMF will be the cell for everything. So understand this very importantly. This is for identical cells. When cells have same EMF and they are connected across in parallel, even if you have 100 cells in parallel, the voltage or total EMF will be EMF E of one cell only. So don't be confused. I'm telling once again it's for the identical cells of same EMF. Here R, battery small r is in parallel. So small r parallel will be 1 by R plus 1 by R up to M by R. So the parallel small resistance will be R by M. So each battery has got EMF E, and the total resistance of the total EMF is E, and total resistance is R by M. So I can just change this circuit and write it like this. I've got a battery of E and internal resistance of R by M in series with a resistor R. So this is my circuit which is finally equivalent one. So I equals to total EMF E by total resistance. These two are in series now. R plus R by M. Take LCM. You get E by MR plus R by M. It goes up. So I becomes ME by MR plus R. So this is going to be my cells in parallel. And I can combine them together by series and parallel. Then you get series and parallel together. This way and that way. So if you have n cells in series, let's imagine E n cells. All are RR. Same n cells in series once again. EMF, 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 RR. Like that, there are m rows. Then you have a resistor. If you have this issue now, then we have a problem. Let's do one at a time now. There are E cells now in series, N cells in series. So first, let them add all the cells because they're in series now. Add them up. So in the whole, this whole one will now become NR. So I'll have a cell of NE, and NR will be the internal resistance. So I'll add them up all, NE and NR. My next will also become same thing now. I get NE, NR. Like that, I have M cells. So I've got the same thing what I got from the before one. So I've got NE cells in parallel, and there are M cells now. So if I ask you what the total EMF now, I told you in parallel, EMF of one cell is the EMF of all cells now. So total EMF of this cell will be NE. Total internal resistance parallel mein, it's 1 by NR plus 1 by NR up to M by N. So parallel resistance will be Nr upon M. Now add them together, the total current will be I equals to EMF NE by total R, which is capital R plus NR upon M. LCM once again, I get M goes up, MNE by MR plus NR. So this is the formula for your current in case of mixed grouping. N cells series, M cells parallel. So it's very easy because all cells are EMF same and it's okay. Now the problem is here. I got two cells of EMF, E1 and E2, but they are not same. R1, R2. This is sending current I1, this is sending current I2. Now we have an issue. The problem is the EMF is not same. What will be the total EMF of this total one? So it was very easy for us in parallel, E was same, okay, now it's not equal. When they are equal, I told you the EMF of the parallel is EMF E1. Now they are not equal. So understand this very clearly. When you have cells in parallel of different EMF, that means EMF is not same, we are sure. But if they are in parallel, the one thing which is going to be constant is going to be your terminal potential difference. So terminal PD of all cells will remain constant. So terminal PD will remain the same. That means the terminal PD of this will be V, this also will be V. So both will have same terminal PD, which is V and V only. So difference between the information I told you before and now, if you have same cells EMF across in parallel, my total EMF will be E. If I have different EMFs in parallel, then the constant value will be your terminal PD, but we have to find the total EMF now, we'll find out that. So I1, I2, if you add them up, it's going to be I1 plus I2 is a total current, I know that. So the terminal voltage of the first cell will be V equals to E1 minus I1 R1. I'm writing V because both are V1. And V, second case will be E2 minus I2 R2. This is the first cell, second cell, both have same V. Do not do the mistake of putting V1, V2, you're finished. So V should be same. So V1, this is V. So now let's do one thing. Let's find out I1 from this. So here this becomes I1 R1 will be equal to E1 minus V, or I1 will be equal to E1 minus V by R1. E1 minus V by R1. Similarly, I2 will be E2 minus V by R2. So these are the two informations I1 and I2 I got. Now add them up because my total current is I1 plus I2. Add them up. So my I will be equal to I1 plus I2. Just add them up. So I got E1 minus V by R1 plus E2 minus V by R2. So what we do is we'll open it up and write this way now. E1 by R1 we'll write, minus V by R1 we'll write, plus E2 by R2 minus V by R2. If I interchange these two values now, what you get? When you interchange these two values now, we get something like E1 by R1. So we'll do one thing. E1 by R1 plus E2 by R2 minus V by R1 minus V by R2. So this is what I get when I change it. So what we do is we will now take LCM of these two. You take LCM now, niche R1 R2 aega. Then this goes up here, E1 R2 plus E2 R1 minus, take V common, minus V common. So this becomes 1 upon R1 minus 1 plus 1 upon R2 because minuses come out. So if you multiply now, minus will come into picture. So this becomes E1 R2 plus E2 R1 upon R1 R2 minus V. Take once again LCM here, R1 plus R2 upon R1 R2. This is going to be equal to I. Great. Now what we do, we interchange these two values now. Take V this side, I that side. So if you do that, what you get? V will come first, V into R1 plus R2 by R1 R2 equals to E1 R2 plus E2 R1 upon R1 R2 minus I will come into picture. Now take this down. Take V there, take this down. When I take this down, what you have is this. When I take this down, this will go this way. They will always get reversed. You are right ulta now. So I'll multiply this with this and this also. So I'll get V equals to, this one is E1 R2 plus E2 R1 upon R1 R2 into, this will go and become R1 R2 upon R1 plus R2. So I'll have this, for this also minus is coming minus I into R1 R2 upon R1 plus R2. That means I have just taken that side, multiplied both. Common leke multiply. So that means you take a bracket, take it out, and if you open it and you get this. Now R1 R2 gets cancelled. So what I get now is V equals to E1 R2 plus E2 R1 upon R1 plus R2 minus I into R1 R2 upon R1 plus R2. That means we get V equals to E minus IR formula only. This E is your total EMF of all the cells. This is the total terminal voltage is common. So if I equate these two values now, this is V, this is I, so this should be R and this should be E. So this should be my total EMF of two cells in parallel, and this is the total resistance of the two cells in parallel. So the total EMF of two cells in parallel will always be equal to E1 R2 plus E2 R1 upon R1 plus R2. So this is going to be the answer for two cells in parallel EMF, and internal resistance total will be R1 R2 upon R1 plus R2. So now understand one thing. Now if you are given in numericals now two cells of different EMFs now, and you want to know the total EMF of the circuit now, it's very simple to find out. For example, I'll give you the information now. This is say 3 volt, 2 ohms, 2 volt, 1 ohm. This is connected to a resistor R. Let's imagine now. The voltage across R. The voltage across R is the total EMF of this system. Total EMF of this thing. So what I do, this is E1, this is E2, this is R1, this is R2. I use the formula now. Total EMF will be E1 R2. E1 R2 plus E2 R1 upon R1 plus R2. So E1 3, R2 is 1 plus E2 is 2, R2 is 2 plus upon 2 plus 1. So this is going to give you 3 plus 2, 5 by 3. So it's very simple that you can find the value easily, but be careful about one thing now. If this should be this way, sorry, this should be same direction. If it's going to be different now, then E1 minus R2 will come into picture. So you got to be very careful about the diagram, otherwise you will get completely mixed up. So this is the first part of the information, and we did about what is Ohm's law, what is resistance, what is your drift velocity, then what is your EMF and terminal PD, what are the factors resistance will get affected of, and what will happen when you put cells in series in parallel and resistance in series in parallel. So this is the first part of the chapter, and we have a second part for Kirchhoff's laws and your potentiometer and meter bridge. So the first part is this much, and the summary of the first part is as follows.